Okay, in the last week we have talked about the system analysis in the time domain at system dynamic. Okay, and so we need to talk about we continue with the ramp response. What is the ramp response, Elida? Huh? Just think about it. What's the meaning of the ramp? Huh? No, it's just like the ramp, which means that this one. This is ramp. Okay? And so this M, and at the 1 unit, we have the M. Okay? This is ramp response. And so, when the function like this one, so the response is different from unit step or the step. Okay, unit step, just remember that the unit step is indicated with the what? With the 1 divided by s, and so we have the constant value at the what? At the graph. Okay, and so we always apply the constant signal. So in order to understand this, suppose that we have this kind of model. Q dot V dot is the velocity, and it's the derivative of velocity is equals to what? The acceleration. And so V and apply to the 1t. Okay? This is the input. This is the V dot plus V. Okay? And so if we assume the V0 is equal to 0, 0 initial condition, and then we can say that it's Q times S times Vs plus Vs, which is equals to what? 1 divided by S square. Okay? 1 divided by S square is the Laplace transformation form of the t. Okay? So, Elida, how we can obtain the Vs in here? We can write to the what? We collect the whole terms, and so 1 s squared times 1 divided by 2s plus 1, right? This is our transfer function applied on the ramp response. Okay? So, how we can solve this problem? Can anyone say that? Yes. We can split into the parts just like this one, the Vs, and so A divided by S squared, B S plus C 2S plus 1, and so the collective term should be equalized with the numerator 1, and so we can solve it, and we will obtain the what? The A, B, and C. But I can write the solution automatically, just like this one, t minus q plus exponential term minus t divided by 2. Okay? This is our form. And so, which one is transient response in here, Hajar? Which one? Which one is transient? And we have also steady state. Yes, why? Yes, but why? Transient means geçici, right? And so, if the t is going to the what? To the infinity value, this goes to the what? 0. And so, what about this? This is steady state, but not a constant steady state right now, right? We have the t. If the t is going to the infinity value, what is the values of the vt? Yes. This is called the ramp response. Okay? And so, if we apply the AND system to the what? To the ramp signals, and so the ramp signals just like this happens in here. And so as we always a steady state error in here. Okay? Okay? İlayda? So, if this is the case, and then we can write another input signals, acceleration response. Acceleration response. Okay? So, just use the same system. Q dot V, Q times V dot plus V, which is equals to what? The 1 times T square right now. Okay? And also we can write the V0 is equals to the 0. Okay? What is the Laplace transform of this equation? Vs 2 times s plus 1, which is equals to what? 2 divided by s over 3. Okay? This is the Laplace transformation of the what? Of our acceleration response. What's the meaning of the acceleration in here, Elida? Just use the previous case. And so what is the meaning of the acceleration? Yeah, but yes, but if the t is going to the infinite value, it always increased, not the constant one, just like this one. See, this is t over q, right? T squared. And so, if this is the case, the Vs is equals to the what? 2 divided by 2s plus 1 s over 3. And so, the solution of this term is equals to what? T squared minus 4t plus 8 plus 8 times e over t divided by 2. Okay? These are the equation. And so, Furkan, what is which part is steady state right now? Left part. Why? Yes. But this one? Huh. Just say in Turkish. Just say in Turkish. It's not diminishing. Okay? But at any case in here, we have t is going to the infinity value. T has always what? Steady state error. Okay? In the later cases, we will call it to the what? The type of the system. If we apply the unit step to the signal or the system, and so we have the type 0, the position, velocity, or the acceleration. These are important because if we want to control the velocity value of any system, and so it's important. If we want to design a control for a position or the velocity has different properties in nature, in the math. Okay? These are important parameters. Yes. Yes, but in a different systems. Okay? So, and 8.2 right now the response of second order system. Later, What is the second order system? Yeah. Yes. Could you give me any example about it? Yes. But we can add the m x dot and c times x dot. Okay. Just continue. And kx. This is the parametric one. You are true. Okay. After. And so, what is the Laplace transform or the transfer function of this system? Hajar. What's the Laplace transform or transfer function of this system? Just say it. Yes. Yes. Yes. And k. And 1. Right? And so this is the same with the what? With inertial system. Right? I times theta dot dot plus c theta dot plus k theta, but in this case torque should be given. And so theta s divided by tau s. Torque s is equal to the what? And so Furkan, say it. This is the same analogy, right? Also, we can write what the electrical system, right? V square Vc dt plus Rc times dVc dt plus Vc, which is equal to what? The applied voltage. And so, what is the VCS, Vs in here? 1. And so, Lida, to say it. Yes. No. R. RCS plus 1. Right? Okay. And so, we should call it, these are the total same system. We can analyze system either is the what? The M, I, L, C. Right? These are identical in the system analysis because we have only an equation, not the physical system. If we choose the phi is equal to the M, and so we can design the L times C is equal to the phi. And so we have the what? The same response at these three kind of system. They are analog, right? So we can write to the what? Just remember that we have the important parameter zeta and Wn value. Remember that? And so this is the damping ratio. This is related to the what? The loss energy. This is the Wn. This is oscillation parameters, right? And so the Vn in the mechanical systems, K divided by M. And so in the Vn is equal to what? G divided by L for a pendulum. Or Vn is equal to what? 1 divided by Lc. Right? See? These are identicals. And so if we define any system with one parameters, and so we can always define anything based on this information. Right? Okay. So how about this one? If this is the case, just remember the first order. For the solution, we can have the Fourier response of what? X dot dot, just like the Elida said, Ax plus B, which is equal to the what? Equals to 0. Why is it equal to the 0? What's your name? Mehmet. Adaş, y should be equals to the 0. Huh? Anyone sure about that? Huh? Because, İlayda, because y should be equals to the 0. Now, yes, the Fourier response is equal to, right? If we have any input parameters in here, and so we have, İlayda, we have which response? Yes, Hajar, thank you for your participation. Okay, answer. What is the root of this equation? Xs s square plus asb. And so, s1 and 2 is equals to what? Who said that? Sen, evet. Türkçe'de böyle bir şey var. Kim dedi? Ben dedi. Deyince herkes anlıyor gerçekten. Kapıda da aynı şey var. Okay. Okay. This is our formula for the what? Square root formula, right? So, what happened if I choose a square greater than 4b? What's our roots right now? Yes, always we have the two, but S1 and S2 are real right now. Okay? Are real because we don't have any imaginary part of this system. And so, what is the R solution? Yes, we can use the trial and solution method, just like in the midterm, right? And so we have the one constant C1 times E S1 T plus C2 times E S2 times T, right? This is our the equation. And so, what about this one? If A square is equal to the 4b, what's the condition of the roots? One root, but yes, repeated root, right? S1, S2, repeated. And so, what is our solution? Looks like C1 plus T times C2. And so we have the one root S1 T, right? This is our solution. And so what is A is equals to 0 and B is greater than 0? Just look at this formula. And so, yes, S is equals to plus minus J W, right? And so, what does our solution look like? XT, yes, thank you. We T, şeyi durduramıyoruz bugün. O WT. And so, Hajar, let's continue. A is not equals to 0 and A square smaller than 4b. What is the R roots? Complex, but we have the real part and the imaginary part. And so we have R plus minus J W. And so it looks like, Hajar, just say it. WT plus C2 cos WT, right? But we have one more parameter. E over huh? No. RT. Okay. We have this 4 to what? To analyze our systems based on this one. Okay. And so if we have the roots or the coefficients of this term, just like this term, if the S1 and S2 is smaller than 0, and so we can say that this signal goes to the what? 0. This one? Yes. This one? Third one? Huh? Period. And which is called the neutral state. So, just remember the previous lesson. We have talked about the stable, unstable, and neutral state. Right? Detaylı. What's the meaning of stable? Or the stability in the control or the system dynamics? No. Yes, but we have this. Huh? Yes, but yes, we have always said the same thing, but we need to define as a mathematics. If time goes to infinity, xt goes to the what? 0 or some constant. We can say that it's stable. Okay? And so, how we can analyze the these terms? Just remember the what? This graph. This is the S plane. Okay? Can anyone remember the S plane? Furkan? Sequence system? Huh? S plane? Okay. So, we should write or place the roots at specific points right now. Okay? And so, what about this one? At this point, the system is equal to what? S minus B plus J W2. Okay? And so, this is equal to the what? B minus B, and so this is equal to, yes, W2, right? This is magnitude, right? Okay. What is the output of this? If we run this system, this is the T, and so xt, what's the look like? I don't know. Yeah. If there are any oscillation in here, oscillation happens in here or not? Happens. Why? Why? Huh? Yes, but why? Yes, if we have imaginary part, we have oscillation. Okay, and so if the time goes to the infinity, this x value goes to the what? 0, right? And so, if we have this information, and so, in this case, we have this kind of output in here, okay? A constant value or 0, okay? If we have the pre-response, and so it goes to the 0. But if you have the forced response, going to the what? The constant. So what about this? S is equal to the what? Minus B plus J W1. And so this is the W1. And so what it is look like? Yes. Oscillation right now is smaller. Right? Why? Yes, W1 is reduced. What about this? What about this? I don't know. What about this? This B. This is the S. Constant. Just like this one. Right? Right? İlayda? Huh? Huh? No. No. At some point from even an initial condition, it's going to the what? To the some constant. But we don't have the any oscillation. Okay? Because İlayda, we don't have the any W1 or W2. Okay? And so we can set what the S is minus A. What does it look like? This is this one or not? A is bigger than B. Yes. Yes, Hacer. Why, Hacer? Okay, what about this? Yes. Good. What about this? This one, right? Exponentially increase right now. Okay? So, what about this point? Just like this one, right? What about this? What's the difference between these two of them, Hacer? Say, Hacer, what's the difference between the W1 and W2 graph? Okay. And so, what about this? This is the S minus A plus J W1. What is the difference between these two graphs right now? Yes, we have the same oscillation, but we have longer period. What about this? Huh? Because the B, for example, 5. Okay? A, for example, 2. And so, if you have the time constant in here, 5, 5, it goes to what? At the same region, for example, 5 seconds. But it has a small value, and so it's slowly decaying. Right? Okay? Just like this. Okay? So, what's the stable region? Which one are called stable? This is stable or not? This region. This region. This region is stable or not? Yeah? Okay. This is called unstable. Right? This region, this is stable. Why? Yes, it's approaching to the what? Some constant. What is this? Natural, not, no, neutral. Neutral is stable. Either we can go to the what? To the infinity or some constant value. Right? So, how we can define these parameters in terms of the what? The oscillation or the natural frequency or the damping ratio. Just remember that. We have the some constant form related to this one. This is like s squared plus 2 times zeta wn s plus wn squared, right? This is our basic form for the what? Second order system. We derive these parameters, right? And so what is the root of these terms? S1 and 2, which is equals to minus zeta w times wn plus minus j times wn times 1 zeta squared, right? See, this one is equals to the real root. This one called the WD, damped frequency, right? Right? So, what is the tau value of this system? Time constant, which is equal to the what? Just remember that. What's the real root in here? İlayda? Yes, zeta times Wn. And so, this is a frequency constant. How we can convert this frequency constant into the time one? Yes, 1 divided by zeta Wn. See? And so, if we have any S-plane, just like this one, and so we can draw or point to this value. And so, what is this value in here? What's the real part of this equation? Huh? Yes. What's the value of this term? Right? And so we have this kind of root in here. And so if we have the positive zeta and wn, and so we can say that this system is stable or not. Stable. But what is the condition of stability in here? What is the condition of the stability for this system? In order to create or satisfy this condition, we need to satisfy that zeta times wn must always be positive. Right? If this is positive, and so we can say that this is stable. Okay? So, let's take a break.